Welcome to the ENME 351 video lecture series. This is part one of a three-part installment on noise and filters. In this lesson, we'll explore the concept of noise. In terms of sensors, noise is considered everything but the signal of interest. And there are various ways in which noise can be introduced into the sensor. So let's consider we have a sensor denoted by the box here, and I have some signal of interest. And this signal is something like a temperature or a pressure or a force, but it's something I'm trying to measure. It's a signal of interest. One way in which noise can make its way into our circuit is right here, and we're going to refer to that as noise 1. And so the signal and this noise 1, they both enter the sensor. And then coming out of the sensor, I have the potential for even more noise to couple into my signal. And this is even before the signal might go to any sort of signal conditioning electronics that I might have. And so this would ultimately be the output from my sensor. It might be something like a current or a voltage. So let's take a look at this first noise source then. This is coming into my sensor along with the signal. So it should have the same units. So this first noise source, this is typically due to things that are going on in the environment in which the sensor is operating. For example, let's consider we have an accelerometer and we're using this in the lab, and the lab happens to be on the first floor of a building right next to a busy highway, right? So there's a potential for vibrations from the cars driving by to couple into the signal. And so I might ultimately be measuring some vibrational component from this noise source from the cars driving by, rather than the measurand of interest that I'm probing with my accelerometer. So this would be an example of noise 1, this first type of noise that can couple in. Noise 2, there's a potential for an even greater number of sources. For example, we might have some cross-sensitivity to other signals. An example here would be a temperature sensitivity, such as with a strain gauge. So if I'm trying to measure strain and my strain gauge is actually susceptible to temperature, I have some sensitivity from another source. And this will show up as noise in my measurement. Noise 2 could also be noise coupled in from other sources. A very common one is 60 hertz EMI interference coming off of the wall. So if your sensor is acting like an antenna and it's near a wall plug or an extension cord, oftentimes you'll see the presence of this 60 hertz noise coupled into your signal. And we can also have noise sources that are just inherent to the sensors or the circuitry used in the sensors itself. An example here would be something like a thermal noise that would show up in, say, a resistive sensor. Now, there are various types of noise, and we need to properly understand these types of noise such that we can address them in the circuits we're using. One very common type of noise is white noise. And white noise, it's a random noise signal, but it has a very flat power spectrum. So if I were to plot power versus frequency, it would be very flat. So white noise is random. Nyquist-Johnson noise also tends to manifest itself in various sensor circuits. So Nyquist-Johnson noise, this is a result of thermal agitation of charge carriers. And this type of noise, it's a thermal agitation that's regardless of the applied voltage to the circuit. A typical example of Nyquist-Johnson noise, let's say I have a resistive sensor. I could consider that as a resistor in series with a voltage source, where this will be V sub n bar, denoting sort of the average noise. And Vn bar squared, that's equal to 4 kBTR times delta F. Now, Kb, that's Boltzmann's constant. That's equal to 1.38 times 10 to the minus 23 joules per Kelvin. T refers to the temperature of which the circuit is operating. R is a nominal resistance. And then delta F, that's the bandwidth. So if you have a resistive sensor, you absolutely have the presence of Nyquist-Johnson noise. Another common noise source that's rather interesting in terms of sensors is shot noise. Shot noise, that's due to the discrete nature of current in a conductor, or if you have an image sensor, it's due to the discrete nature of the photons in the image sensor. So if you have a camera that your images look noisy, some component of that noise will be due to shot noise. So this Vn bar, that's really describing the RMS noise experienced by the sensor. And recall RMS, that's the root mean square. So Vn bar, that's one metric by which we describe the noise in our system. Another metric that's oftentimes more commonly referred to, actually, is the signal-to-noise ratio, or SNR for short. So SNR, that's equal to 20 times the log base 10 of my signal amplitude over my noise amplitude. So something like the RMS of my signal divided by the RMS of my noise, and that's commonly provided in units of decibels. As an example, let's consider a signal for coming off of a sensor that's about 10 times the noise level in that sensor. I might write this as the RMS voltage of my signal is 10 times the RMS voltage of my noise. This will result in an SNR of 20 dB. I'd have a factor of 10 in my signal-to-noise ratio. So log base 10 of 10 is 1 times 20 gives me an SNR of 20 decibels. Now, typical metrics you'll see for SNR, typically something like an SNR of 3, and that'll be the actual linear, if you will, ratio of the RMS signal over the RMS noise, and then commonly something on the order of 10, right? So a factor of 10 here, as in our example, gives us an SNR of 20 dB. So these are common SNR metrics that you'll see for various sensors.